So obviously we will start with today we will start with the recap of day 2, and then as promised, I will show you some machine learning applications using, let's say, PyROOT and then uproot. Okay. So then we will finish this 3 set of lectures. Before going into the details, let me put it in full screen. Okay. Before going into the details, I would like to, or before going into the tutorial part or running the real code to do everything that we are learning here, I would like to give you an overview of what we are trying to do. So in modern day analysis, kind of this is the workflow that we generally follow. Okay, it's not mandatory, obviously. This is not a hard and fast, workflow which everybody has to follow, but it's like a standard workflow that we generally follow when we analyze the data using either PyROOT or other software which are available. So if you look at the chain of steps in the first row, which says that you have a data set and you access the data set. And as we have seen that to do that, we can use uproot. Yesterday, we saw that we can use uproot to access the data. That means we can open the data and read the data and read everything that we have inside the data, at least the ones which are translated into some kind of a Pythonic object. As I already mentioned that for uproot, there has to be a conversion from the, okay, let me turn on my video. Yes. Making my background a bit black. Okay, sorry. So what I was saying is what we are trying here is using uproot, we are converting the C++ object which is stored inside root into a Python object. That means the object that it is returning is a Python class, right? And as we have seen yesterday, that when we were reading a standard vector of C++ and we were reading it using uproot, it was converting it into an awkward array, right? Or there are other possibilities, of course, that we can convert it into a NumPy array, or we can also convert the input data into, let's say, pandas data frame. But everything here is Python object, right? So we are translating the C++ object into a Pythonic object. Whereas using uproot, it was different. We were still creating C++ object, but there was a proxy in Python which we were using to talk to the C++ object. We were sending some instructions that, okay, we have a histogram, which is a C++ object, th1, h1f, let's say, float, one-dimensional histogram. So we were still creating C++ th1f, but we have a Python proxy which was talking to that th1f object. And when we said fill, then it was basically filling the C++ object, or it was using the fill method of the C++ th1f object. So as you can understand probably now that there is a difference between the two. And that was the main goal for me to help you to understand this basic difference between uproot and PyROOT, obviously. But otherwise, as I have already said, that PyROOT is not only reading the root files and accessing the data or storing the data in a root file, but it can also do whole lot of things that uproot itself cannot do, but it needs the help of other softwares to do that, right? So it is only doing IO, input output, using the root data, and uproot doesn't depend on, I hope you remember this part, sorry. That uproot has no dependence on root. That means even if you do not have root in your computer, you can still run uproot. Whereas PyROOT is obviously a package inside, or PyROOT is not an independent package, but it is inside root. It comes with root, right? So part of root. But whereas uproot depends on awkward array, which depends on pandas, NumPy, and etc., or it can directly use C++ in the backend, right? As NumPy or pandas do. Now, okay, let's come back to this flow chart. As you can see that you first access the data, then you make some selections. We have seen that we can, using Python, at least as we are discussing about PyROOT and uproot, let's stick to Python. So we apply some selections on the array, right? We can say that, okay, I only consider some elements of the array, not all. Maybe I want to select only those events where I have photons with momentum greater than 25 GeV. We have seen yesterday, right? So this kind of selections we can make at some stage, and then comes the machine learning part. So for any kind of machine learning application, at least where we are doing supervised learning, that means we use the data which we already have to train the machine, to train the network, to train the algorithm. So that is called supervised learning. So we have some labeled data. That means we know that these are Higgs, these events are Higgs events, and these events are non-Higgs events. Let's say QCD events or some other kind of physics processes, right? We know, and only how can we know? Obviously, using some Monte Carlo simulation, we can simulate some Higgs events and simulate some non-Higgs events. And then there we know, because that we have generated those samples. And that is why we are calling it labeled dataset. And when we have labeled datasets, then we can do supervised learning. That means you train some algorithm, machine learning algorithm, which will learn from the labeled dataset. And after it has learned the discrimination between, or difference between the two datasets, let's say one is Higgs dataset, one is non-Higgs dataset. If now you give him or her an unknown data, then it can tell you what is the probability that this unknown data is coming from Higgs-like process, or it is coming from non-Higgs-like process. So it will give you these probabilities, right? So that is the idea of a supervised learning, that you train with some dataset and then you apply it to some unknown dataset and try to understand. And what can be the unknown dataset? Obviously, unknown dataset means that a dataset where you don't know the levels, which is actually the data that we produce at LHC, right? So when we collide two protons, or leads or other ions, we do not know what is going on in each event. We can probabilistically say that, okay, so according to the nature of this event, characteristics of this event, we can say that this event has a high probability of being a Higgs-like event, right? But obviously, there is also a probability of this event being a non-Higgs-like event. So we cannot say for sure that this is Higgs. And that part is this blue and then next green. So first you have the blue part, which means that you obtain those features of the data which you know are different between the two classes that you want to classify, to discriminate, right? So Higgs and non-Higgs. So you have two classes of events and you want to discriminate between these two. Now for that, you have come up with some, let's say, variables which you know are differently distributed or coming from a different probability distribution function. And if they are coming from a different probability distribution function, if they have clear separation, then it is easy for you by eye to consider that variable as, to predict if an unknown event is coming from Higgs-like process or non-Higgs-like process. For example, let me give you a thought experiment. Let's say that you do think about these proton-proton collisions happening at LHC, and then there is a variable called X, and you know from your theoretical prediction or Monte Carlo prediction that this X variable should be distributed as a Gaussian with a mean of, let's say, 125 GeV and width of 3 GeV. Okay, and this is the distribution of X which you, from theory, you expect in the Higgs-like events, whereas in the non-Higgs-like events, let's say QCD events, you expect this X to be distributed as an exponential, okay, which we saw yesterday in the example. So now think that, okay, if which obviously exponential has the one parameter of this, so e to the power minus lambda x or 1 by lambda x, whatever. So that parameter, and depending on the lambda, it will fall sharply or it will be almost flat. But the point is that they have different distributions. Now, suppose you do the real collision and you find one event whose X value is 125 GeV. But then obviously there is a probability of that event being a Higgs event, and also there is a probability of that event being a non-Higgs event, because both, let's say, the exponential and the Gaussian, they have some probability at X equal to 125. Okay, but let's say there is an event where the value of X is 1000 GeV, or not GeV, but any unit. Let's say X equal to 1000. Now, as I said, that in Higgs-like event, it's a Gaussian with mean 125 GeV and standard deviation 3 GeV. So it is highly, it is very unexpected that event where X is 1000 is not a Higgs-like event, because there the probability, according to this Gaussian, of mean 125 GeV, standard deviation 3 GeV is very low. So we can for sure say that X equal to 1000, this event is non-Higgs-like event. So X is a feature. We can, in machine learning language, we call them as features. Now, obviously, X can be one feature, but you can have multiple features, which you can use to classify between two classes, to do the discrimination between the classes, right? So that part is done. So you decide the features, which is done here after you applied the selection, and then you train your model. As obviously our discussion is not on machine learning, exactly machine learning. So I'm not going deep into how machine learning works and what are the different algorithms. Obviously, those things you will learn in future. But probably you may know about some of the algorithms, like maybe boosted decision trees or neural networks and etc. So you use them here. For example, there is one package called XGBoost, Extreme Gradient Boost. So that is a package. So all these are packages. So you use uproot to access, then Coffea to apply the selection, and then you use awkward array to get the features, and then you use XGBoost to train the model using the input features, and then ultimately you store the model into some kind of a data set, or not data set but a file, a format. Okay, and here for example, one can use NVIDIA to do, to use the GPU to do the training, of course, right? So you can use CPU, GPU, anything you like for the training. Now, once you have the model and you have stored the model, then you repeat the analysis. But obviously, as you can see, that this first part of your analysis, you didn't, you do not need all the physics processes or all the events that is important for your analysis. You only select those events which you want to classify. You can leave everything else outside, right? So that is why this is the first part. And then you have the part where you have all the data sets, all the data that you use in your final statistical analysis. You access them, and then you again apply the selection, event selection. For them, you use the same software. And now, apart from in contrast with the previous flow, that where you just stopped there, that you trained the model and stored the model, now you use the model, you read the model, and you use the information that this machine learning model gives you. That means, suppose you can say, oh, I know that for sure if X is above 150 GeV and X is below 100 GeV, they are always non-Higgs-like particles or processes. So let's throw them away. So here you infer the machine learning model, and then you get the values of, using the X, you get some values of the score of your machine learning model, which tells you that if these events, some events are Higgs-like or non-Higgs-like, and you can make selections on that variable to discriminate or to throw away the events which you do not like, or events that you do not need at the end for your final parameter estimation, right? So where you want to measure the mass of Higgs, let's say. So the main goal is, if you want to know the mass of Higgs, you reduce all other kind of processes from your data as much as possible, so that you only end up with mostly Higgs-like event. And for that, you infer this machine learning model and apply the selection again on that output score, and then you make histograms, do statistical modeling. That means, you remember yesterday we built the signal model and background model using polynomial and Gaussian. And so signal using Gaussian and background using polynomial. So you make those models and then do your statistical analysis. That means at the end, you measure the parameter of interest, right? So what you want to measure, either mass of Higgs or if there is any SUSY particle there or not, etc., right? So so all these kind of things we try to do at the end. So this is the analysis flow. So, and as you can see, using PyROOT or root, we can go all the way up to, you know, the final plot. So you do not need any other software. I mean, or even if you, I mean, even if you need, they're already integrated inside. Okay, so you remember that it is not that root has no dependencies. Of course, when you install root, you already install all the dependencies on which are important to run root, right? Whereas that is why some people prefer using uproot, because root is a big package. It has a lot of dependencies. That means if you install root, you have to install many packages. Now, obviously, when you use root, you do not understand which package you are using, but actually it is inside root who decides which package to use where or for which purpose, right? So, whereas uproot is a very small package, very small tool, which just give you the input output, that means read and write of the root files, or you access the data. Now, that is why it is small, that is why it is lightweight. If you install uproot, you do not need to install a whole lot of other packages, whereas if you install root, you have to install many other dependencies. Now, then the other part is, then obviously, if you only install uproot, you cannot do everything. Then you have to install more packages separately, but there you have the choice that I want to use this package or that package for statistical analysis, let's say. But whereas in root, you do not have that choice. Whatever is already there integrated with root, you can only use those packages, but you cannot go outside that. So these are the differences between the two. Now, let's go to the problems. If you have any question, you can raise your hand. Otherwise, I will. Okay.
Can I ask one question?
Sure.
Sir, here on the slide where there is the last cartoon on the
Yes.
upper data flow where you mentioned that while selecting the models you have to choose a CPU or a GPU. So I mean,
Not selecting. I'm sorry. Not to select the model. Of course,
Mhm.
it's true. So you have, when you do the training, it's a lot of computation, right? So there are multiple matrices which are being multiplied again and again. Okay. And this kind of computation is obviously done on either CPU or GPU. So that is what I was trying to say, that you can use either GPU, CPU to train your model, right?
Okay. So which means the model is, I mean, already selected by me, but I have a choice to perform this operation on CPU or maybe
Yes.
on. Okay.
Yes. But yeah, the other part which I mean, this as you were saying, that this model storing the model, okay, there are many modern techniques. These techniques are used because nowadays people can have many different packages to train their model, let's say. Now, suppose I'm using PyROOT, you are using uproot, or you are using some other package, scikit-learn. And now, at the end, our goal is the same, let's say, to discover a new particle, for example. Now, suppose that is our goal, but I am working with you, and you are sending me some model which I want to use in my analysis. But I am using a different software than yours. Then there will be a problem, because if the format in which you write your model is not what my software understands, then there will be problem because I will not be able to use your model.
Correct.
So that is why people have come up with ideas that, okay, let's put these models in a kind of format which all other softwares, they must follow some rules so that they can make inference using these models, or they can, let's say, translate these models into some format which they understand, so
Okay.
that any model which you train or I train using any software, at the end we can share our models, basically, right? So that is the idea of using this this part, which is called select best models for inference.
Okay, sir, it is clear.
Okay. Okay, then let me go to the here. So before I start, I would like to tell some of you who are actually having problem in running these Jupyter notebooks. So first of all, I hope you remember that I always told you that before you open the Jupyter notebook, you should see that currently you are using the right conda environment where root, uproot, these things are installed, right? That is the first thing that you should check. And if it is not, you are not in that environment, then you should activate that, right? That is what I said. Activate, in my case, it is MacRoot, but I'm already in that environment. So for those who are having problem, I just would like to mention that make sure that you did this. Okay. Let's say even after you do that, you still face some problem when you, let's say you are trying to run some of the exercises. Okay. So let's say for this one. Now, if you open one of the Jupyter notebook and you see, some of you are saying that you see that your kernel is again and again, crashing, basically. There can be many reasons for that. But one of them is obviously you should make sure that you are using the correct kernel. And if you are not, so from where you can see that? You can see that from here, right? In the top right corner, just below logout, there is a part where it shows which kernel you are using at the moment. So if you see that you are not using the environment which you have created using conda, then you should switch to the environment. Kernel is basically the corresponding conda environment that you want to load here. Okay. So like if I click here, and obviously you can, even though you have, let's say, one environment of conda, but you can create multiple kernels out of that environment. You can give them different names and etc. But I'm not going into that now. So you should choose the proper kernel before you run your code. So these are the two things that are minimum, and maybe for some of you this can solve the problem that you are facing, but obviously for some others the problem may remain. And for that there can be many reasons. As I said, some people are trying to install everything in Windows and etc., which are always difficult, and you have to somehow go to internet and try to find solution to them. Obviously I'm going to help you as much as possible, but again, so time is limited and we can't discuss everything probably together. So let us start. Okay, so a bit of recap of what we have learned so far. Okay, here I'm not going through uproot in this exercise, but maybe I can open one exercise from yesterday just to remind you what we have done. So using uproot, as you can see, we open a file, we can open a file, and then we can get the tree which was stored inside the file. And if we do tshow, then it's going to show the original type name of these branches which are stored inside the TTree. And it also shows the uproot interpretation of these branches. That means how uproot is interpreting these branches. And as we remember that they are basically interpreted as jagged arrays, and they are basically using this awkward package. And as I already discussed with you, that your arrays can have different number of elements. That's why for each row, that means for each event, they may have different number of elements, and that's why they are called jagged. They are not a kind of a rectangular sheet. Okay, so and then you can do everything that you do using normal NumPy arrays, right? So you do :2, that means you are going to see only the first two elements. And you can, okay, you do not need to load the whole array at once. You can say, okay, I only want to load starting from 10 to 20. So these kind of things can be done using uproot, that you can read a file and there is a tree inside, you read the tree and you can get all the data that is inside the tree in terms of branches, let's say. And obviously, as you can see, that there is a translation between this std vector float to jagged arrays. But who is doing this? Obviously, uproot is doing this. Now the question is, suppose in the input file, that means in the root file, I have some data type which is unknown to uproot. For example, you create your own data type. Let's say my data. That's a struct, let's say, that you create. Okay, and you create an object of that my data. So as you do float a, you can do my data a, let's say, and a is now an object of type my data. Okay, and then if you store some information in that my data object, let's say, and you store that data inside a tree, and then store that tree inside a root file. We could do that, but let's not do it to save some time. So, but the idea is that suppose you create a data type, or you use a class which is not standard, right? And then you store that data in the root file and open the data using uproot. What it will do? The answer is obviously it's not going to understand what is that. So it will not be able to give you an array of that object, because for uproot, it can only translate those words for which it knows the meaning in Python, right? It cannot translate every word which are possible. It can only translate those words which it knows how to translate, right? So this is obviously one limitation. But then you can ask, can root do that? Obviously, if you want root to know that there is a class called my data, then you should also load that my data object or my data or a header file or something where you define what is my data, and then only root will also know that there is something called my data. Otherwise, root will also complain that in this root file, in this tree, there is a branch which has a type which I don't understand. Okay, so for both uproot and root, you must tell them that, okay, so there is a new type of object which you may not know, but you can learn it from this header file. Okay, but obviously using uproot, it will not be like that. So for that, you probably have to create a class in Python, and then hopefully it will be able to understand what it means. But still, it's not straightforward. But whereas in root, it's a bit simpler, I will say. But okay, so this is how we used uproot yesterday. Now if I go to the first exercise, or yes, the recap exercise. So I didn't mention too many things about awkward, because obviously these lectures are not on awkward, but still, as you see that there is a limitation of uproot, that it doesn't go ahead of just reading and writing files. So if you want to do something with the file that you read using uproot, obviously you should learn what is awkward or what is NumPy or pandas, right? So here I give you some example, like for awkward, obviously, because the developer of uproot and awkward are same, and the person who developed who developed uproot, he realized that we should use some kind of a array based programming which has this jagged structure, because in high energy physics, which is not like always required outside high energy physics, but in high energy physics we know that we need everything that we can do using NumPy or pandas. That means basically array based programming. We can kind of, yesterday we saw that we can, okay, I will come to that. But so basically he developed this awkward, and it's good to learn awkward, because if you want to use uproot, you have to install awkward, and that means you have, whenever you install uproot, you have these two softwares, so you can learn awkward to do manipulations or read the data, and etc., apply selections, and etc. I already have shown you that that part in the chart of modern analysis flow. So as you can see that if you, again, we are importing awkward, and then we can create an array using this awkward.array, and we are passing a list. I hope you already learned about this. And we are passing a list, and that will return an awkward array. And as you can see, I mean, it is exactly same as what we do using NumPy. So we just say np.array, and then we pass the list of numbers or list of anything that we want, and that will create a NumPy array. Basically, awkward is doing the same thing. And then the other possibility is that you have a different shape of the array, right? So like in this case, you had for example 1, 0 or something like that, where you have 1 row and 0 columns. Oh, sorry, not 0, sorry, 1, 2, 3, 4, 5 columns. So 1, 5. Whereas here, what will you say? Because this is a list of list, right? And then if you try to get the shape of this, let's say, oh, okay, so maybe it's only shape. Sorry, no, it's not same as NumPy. Maybe it has some other did I use it somewhere? No. Is it capital S? No, it's not same as NumPy, but okay. So
Sir, you have to
let's see that,
import NumPy as a NumPy, then only it will work, correct?
hopefully, yes. Then you have to convert this awkward array into NumPy array. But okay, so let's not go into that. So I hope there must be something. Okay, let's look for it. Awkward array shape. Okay, you can use show, but is there anything called shape? Okay. So no, there is nothing called SEP in, at least I couldn't find SEP in awkward. But yeah, as we know, we obviously have SEP in NumPy, but then we have to convert the awkward array into NumPy and then we can get the SEP. But whereas obviously we can use this, so probably no, it just shows that the type. No. Okay, forget. Yes, right here. So, okay, let's not do that.
Sir, will it be type dot show? Then it will say, I think it will show what
It will only show the type, right? So it's not going to show the shape, for example. But okay, let's forget about it. Okay, this is a list. Okay, this is a list, but then maybe let me see again if this is possible. Maybe it will work. I don't know. Though I couldn't find it. Oh yes.
Oh, no brackets, no brackets. It will be just array 2 dot shape.
Okay, maybe. Thank you. No. So probably there is nothing called shape. Okay, no, there is nothing called shape here. Okay, good. No problem. So by the way, so you have a nested list and you can have single list and you can store them inside the arrays. And then as you have already done with NumPy, so if you want to access a certain element of the list, you can just say 0 or 1 to 4, right? So that will give you the some elements of the list, right? So as you can see, it's giving 2, 3, 4, 2, 3, 4, because you asked for 1 to 4, right? Then this is very interesting, and that is why I like Python, which is, so as if you are hopefully you have already learned, so I'm not going into the details, but as if you are applying this selection on a single variable, a single valued variable, right? But whereas you know that this array is not a single value, but it has multiple elements. So basically this greater than 3 condition is being applied on each of the elements, and it's going to return for which element it is true and for which element it is false, right? So as you can see, so for some elements it's true, some elements it's false, because when you said greater than 3, and obviously only these last 2 elements 4 and 5 will be true, otherwise everything is false. And then you pass that list of true and false to this array 1, and it's only going to return the last 2 elements, because only for last 2 elements it's true. Then you can also concatenate, let's say, 2 arrays, as you can see, the same as you can do in NumPy. But suppose you have this kind of a list with single digits and then lists, so it's kind of different type of data saved in the list, right? So what we can try is we can flatten the array, and that way at the end you will get a list with kind of, you can call it a, hopefully you know about set. So it's going to return all individual elements, but it is not going to repeat any element, right? So it's not going to give you 1, 2, 3 and again 1, 2, 3 here and again 4, 5 here, something like that. What it is going to return is the unique elements, right? So 1, 2, 3, 4, 5, 6, 7, 8. Again, if you have a nested list, let's say 1, 2, 3, 4, 5, 6, 7, 8, which are, again, these are arrays with jaggedness, right? So some elements, some array has 3 elements, some array has 2 elements, and again 3 elements. So it changes from array to array, right? So that's why we use awkward. So, and then you convert that to awkward array, and then, yeah, this is an interesting feature of awkward array, that if you say num, then, and then you pass this array, then it's basically going to show you the inner lengths, right? The length of each of the individual arrays. So that means first array has length 3, second array has length 2, third array has length 3, 3, 2, 3, right? So, oh, I don't know if you can see my screen properly, but let me zoom it a bit. So, yeah, that's what you can do. So if you use the num method of awkward num function, and then you can also have max function, okay, that will return you, as you can see, we are not passing the whole array, we are passing inner lengths. That means this will return for which inside this awkward array, for which array has the maximum number of elements, right? So here we have 2. So max length will become 3, basically. 3, we have 3 elements in this list and this list. Okay, then another thing, obviously, these are just to show you what can be done. There are many other things which can be done. These are obviously some small examples. Like, let's say you have a matrix and you want to transpose the matrix, right? So you can do that also. So what you do is, let's say you first create empty lists, okay, and you already got the max length, and that means you have, so you cannot transpose a matrix with, let's say, variable number of rows and columns, right? So you must have same number of rows and columns. So that is why what you create is you take the maximum number of columns and maximum number of rows, let's say, which you already know from here, so which is 3, and maximum number of columns is 3, and then you create empty lists, right, from 0, 1, 2, right? So you have created 3 lists, and then what you do, you loop over the array. Array means the awkward array, and then you get each of these lists inside the array, or arrays inside the array. That means in the first loop, it will be this one, 1, 2, 3. And then what you are doing, you are enumerating over that list, this 1, 2, 3 list. You know what is the difference between the for loop, which you do like this, or you do like this. So here the loop will be, it will return every time this sublist will be the element of that array. Whereas if you do enumerate, it will not only return the element of that array, which is here value, but it will also return the position of that value, position of that element, right? So let's say the first element of this list, that means 1, 2, 3 list, is 1. So it will return 1, which is the value, and the position of 1, which is 0, right? So 0, 1, that will be the first iteration of this for loop. Then what you are doing, so you are doing transposed, then in the 0th position of transposed, right? So that means the first list inside the transposed nested list. So because this is a nested list, right? So first list of this nested list will have the value which you are inserting from the original array, right? So like this, you are appending these values for each list, and then what you are trying to do, you are doing the transpose. So this becomes your transposed list, and then you again make an awkward array using that, and you show them. And this is your original array, and this is the transposed array, right? But the thing is, obviously, this is kind of I played something with awkward and NumPy and etc. and Python list, but surely this is not this is where it is not limited. Obviously, there can be many other things that it can do, but for the moment, let's stop here. And if you have any question, you can raise your hand. Otherwise, we will go to the next next exercise. Okay, I see some message. Oh no, this is some old message. Okay, do you have any question? Okay, I don't see any. Okay, let's go to the second exercise. Let's go to the second exercise, which is this exercise 1, Higgs discrimination. So yesterday we saw how we discriminate between no, sorry, not discriminate, how we access the data from a file, root file, and then we can fit the data, fit the distribution of one of the branches, or we can define new variables. So for that, we used R data frame. I hope you remember that we used R data frame to load a data, and then we define new columns in the data, and then we filtered the data set, the columns, or the whole data frame. We filtered the data frame by applying some selections on some of the columns. So all these kind of things we have done. Now, today, what we would like to do is, again, we access the data, but use it for some machine learning application. Okay, so let's go to the exercise. Okay, so as I said, that we are trying to classify two kinds of events. One is the Higgs boson events, and another kind is non-Higgs boson events. I'm not going into the details of physics here, because that will obviously take some time to discuss. But here our purpose is to understand how we can use PyROOT or uproot, how PyROOT and uproot can help us to do this, basically. Obviously, it's not only PyROOT and uproot, but we need more many other packages. In some cases, not in case of PyROOT, but mainly in case of uproot, we need other packages. But at least what I would like to show you, that using uproot or PyROOT, how can you train some networks, some algorithms, right? So here we are going to use some data set which was used for this paper, and they are Monte Carlo simulations. As I mentioned, that if you want to do some supervised learning, we generally use Monte Carlo simulations, because there you know exactly which process is what, which data set is what, right? And each of these simulations that we have, one for Higgs and one for background, they have 21 features or 21 variables or branches, right, stored inside them. And okay, so they are stored starting from the column 2 to 22, which is not important in our case, and they represent the kinematic properties of some particles that we measured in the detector. Okay, and it has been seen, again, we are not going into the details of an analysis. So just imagine that out of these 21, only 7 features are important or are discriminating between the Higgs-like and non-Higgs-like events. So you do not need all the 21 features, but only 7 features are enough to discriminate between the two. Okay, so that is what we would like to do. But obviously, the benchmark result was achieved by using BDT or 5-layer neural network. But here, today we are not going to do that because that will take long time, and that is obviously also not the purpose of today's exercise. It is only to show you how PyROOT or uproot can be used. So what I'm doing, I'm importing root as usual, and I'm importing the OS, which, okay, there is, we will come to that, why we need the OS. But okay, so then there is a package, or there is a sub package you can call inside root, which is called TMVA. Okay, as you already have seen in root, every package or class, they start with T, right? A capital T. So this is not a exception. So it also starts with T, but then the next three letters, MVA, multivariate analysis, right? So that is the package. So this package in root, it is very popular, and people are using it for many years, like even 15 or 10 years. And this is very robust package and very useful package. So I would request you to learn about it if you want to work inside energy physics community. Now, there can be multiple kind of algorithms which can discriminate between two classes. Okay, so as I already said, that probably not all of you know about what is a neural network and what is a boosted decision tree, or what are other kinds of algorithms. So I will not go into the details of algorithms. Okay, as I said, that obviously this is what you are going to learn in the school, right? So that is why I'm not going to spend time on explaining the algorithms. I hope you will learn them during the school, but here I'm going to show you how to use these two packages and then train this kind of algorithms. And today, I mean, obviously you can use any of them, but today we are going to use only two algorithms. One is called Fisher discriminant. Again, I'm not going to go into the details of how this algorithm works. If you want, we can spend some other time to discuss about it or discuss each of them. But today, I'm just going to tell you that this Fisher discriminant tries to separate two classes by a plane. Okay, you can ask from where this plane comes. So you can think this problem as, like, suppose you have 7 features or 7 variables which you think can discriminate between Higgs and non-Higgs like events. So these 7 variables, then you can imagine a 7-dimensional space, right, of these variables. And then you will see that if these 7 variables can be used as some discriminating features for Higgs-like and non-Higgs-like events, then in this 7-dimensional space, you will see 2 clusters of events. One, which is the Higgs-like event. So that cluster of events will be in one place in this 7-dimensional space. And the other cluster of events, which are non-Higgs-like events, will be somewhere else in this 7-dimensional phase space. So if you imagine, for example, again, come back to 1 dimension, because 7 dimension is hard to imagine. So if we come back to 1 dimension, okay, I will probably come to the explanation a bit later, because for that I can show, okay, I can already show you some plot, because there is no problem. Okay. For example, look at this plot. Okay, even though this is not very good discrimination between the red and the black. Red is the class of Higgs-like event and black is the class of non-Higgs-like event. And obviously, as you can see, that these variables or these features are not very good in separating the two classes. But imagine that you have one variable which has most of the events for Higgs-like events. It is distributed near 1, let's say, a peak near 1, whereas the same variable has a value of, let's say, 5 for non-Higgs-like events. So that, and it's peaking around 5 here. And then you have a clear separation between the two. And you can imagine a straight line or a single cut on this variable. And you can separate the two classes of events by applying that cut. Now you can optimize where you want to apply that cut based on some criteria. But that is going to be a single cut. Now, if you go to a two-dimensional picture, so where you have two variables, then you can imagine a straight line which you are trying to construct in this Fisher discriminant. So you are trying to construct a straight line which can discriminate between the two lumps of events, one for Higgs-like, one for non-Higgs-like, right? So the idea is to train this classifier so that you can find the best straight line which can discriminate between the two classes. Again, if you go to higher dimension, then this straight line will become a plane in that higher dimension. And you try to separate the two clusters of events in that higher dimension using a plane. And you want to identify the plane or try to find the plane which can do the best job to classify between these two classes. So any value above this plane will be considered, let's say, as Higgs-like, and any value below this plane will be considered as non-Higgs-like, right? So this is the main idea of this Fisher discriminant, okay? And multi-layer perceptron, the idea is similar. Obviously, algorithm is different. For Fisher discriminant, we use likelihood ratio, whereas for the multi-layer perceptron, it's totally different. It uses this, you are going to learn about that neural network. So there you will learn. But the idea is that there it's possible that if you use two variables and you are using Fisher discriminant, you are imagining one straight line which could discriminate between the two classes. But it's possible that the best discriminating condition may not be a straight line but can be a curve. Okay, so suppose you have two classes which are very close to each other. Okay, they are not very separate, where you can just imagine a straight line and can discriminate between the two classes, but they are very close to each other, they are overlapping with each other. So then it's not a straight line, but maybe you can define some other shape of boundary which will better discriminate, right? So that can be achieved using multi-layer perceptron or BDT or other kinds of algorithms. But okay, again, with this I will stop here, and then okay, what we are trying to do, I am already.
Sir, can I have one
Yes,
question?
sure.
Just now what you discussed, I mean, in the phase space. So, I mean, to start with, we will have a random set of events which will have Higgs-like properties and non-Higgs-like properties. The job of this discriminator will be to draw this plane or to draw this line or maybe the curve. Correct?
No, initially it's not unknown. Obviously, during the training process, you know that these are Higgs-like and these are not like, but these are Higgs and these are non-Higgs events, right?
Okay. Okay.
So when you do the training, you know which are Higgs-like and which are non-Higgs-like. But again, whenever I say that we know which one is Higgs-like and which one is non-Higgs-like, I mean that we are doing a supervised learning, right? So it's not unsupervised.
Yeah,
There is another way of doing this where you do not know, as you were saying, we do not know what is Higgs-like and what is non-Higgs-like. So that's a different way of doing it. But here we are only considering supervised learning. So now what I'm doing here, I'm already getting the T file, class as T file, so that I do not need to write all the time root.tfile, as you all know. We can do this. Then there is a file called Higgs_data.root, which was used by this paper, and they have saved this file in this CERN page, which is for root. So if you, okay, so then this you have to know, obviously, where this file is and what is the name of the file, right? And then once you have that, then what you can do is, this is a good application of root, that if you do root.gsystem.access path name and then provide the name of the file, let's say input file, if it finds that this file is there in the current directory, it's going to return false. Okay, that means it could find the file, it's going to return false. And if it can't find the file in the local directory, it will return true. That means if this is true, that means this file is not present locally, right? Then what it is going to do, it is going to okay, this is just a log, and this is also irrelevant here. So basically it tries to open the file, right, using the link. So input file link, so it uses the link now to open the file. Otherwise, if the file is already available locally, it's going to open it normally. It's not going to download the file, right? So that, okay, that's one feature of root. So now as the file is already there in my computer, so it didn't download, and that's why it didn't print all these things, all the logs, but it just opened the file, right? Now I have in this input file, I have this higs_data.root. Okay, again, like yesterday, we can check using this ls what are the things present inside this file. And as you can see, there are two TTrees. One is called sig tree, one is called background tree, right? And what we can do, as we did yesterday, we can load that sig tree into, we can access that TTree, which is called sig tree. And this is the Python proxy, which is signal tree. I named this signal tree, and I named the background TTree as background tree. And then if you want to check what are the branches inside these trees, you can again do this print, and it's going to show you that there are many, many branches. How many branches? There are basically 28 branches, right? And out of these 28, obviously 7 features are important. Whereas from 2 to 22, let's go and check. So what is 2 and what is 22? So 2 is lepton eta. 2 in this case, I think 2 is not here, it starts from 0. So this one is the second column. So which is lepton pt, lepton eta. So in these events, you have some lepton. You don't know, here it is not mentioned which lepton it is, but you have some lepton, and you have the kinematic variables. That means the transverse momentum. Pt means the transverse momentum, eta means the pseudo rapidity, and phi. Then you have, maybe some of you know, but some of you don't know, that there is something called missing energy. I'm not going to obviously describe what it is, but later if we want, we can discuss. So there are a whole lot of things like jet1 pt, jet1 eta, jet1 phi. Okay, there is something called b tag. I'm not going to describe that here because that's not the scope of these lectures. So basically you have many, many variables. Now let's stop here. This is the 22nd. So this is the 23rd. So they said that 2 to 22. So 2 to 22, that means up to here. So that means 1st to 21st here. So until here, everything was, according to them, kinematic variables, though I saw some of them which are not, but okay, it's fine. Now you, starting from 22, you see there are some m_jj, m_jjj, and etc. m_lv. So these are basically the invariant masses of the 2 jets, invariant masses of the 3 jets, invariant masses of the lepton and the neutrino. By the way, so this missing transverse energy can be considered as neutrino, but obviously this missing transverse energy can be there even if there is no neutrino. But for the moment, let's consider missing transverse energy as neutrino, because as you know, that neutrino almost doesn't interact with anything, and that's why they leave no signature in the detector. So that's why we call it missing. Okay, something is missing in the detector, and we call that as neutrino. Okay, that part of the energy as neutrino. So up to this 28, there are all these mass variables, right? Invariant mass variables, but they are the invariant mass of different things: jet, lepton, and neutrino. 2 B jets, and it can be the invariant mass between W boson and 2 B jets, 2 W boson and 2 B jets, etc. and etc. Okay, all these things which are obviously not what we were interested in. So now if you, okay, so this is also how you can also print the names of the branches. And we have already checked that these are the branches which were present. So what we can do is we can, okay, let's create a list of strings. And these strings are not any other string, but obviously the names of the branches inside the tree. Lepton PT, lepton eta, 5, first 3 branches, right? And as I said, that if you want to look at these distributions of these variables, these branches, obviously you have to create histograms, right? You have to create histograms, and then you have to draw those histograms on a canvas, root canvas. In this case, we are using, we can use obviously other packages, but for this purpose, we are only concentrating on PyROOT. So as you can see, this is how you can create a canvas. We discussed this yesterday, but there is something new. So if we want to draw multiple histograms in the same canvas, what we can do is we can divide the whole canvas into multiple blocks, and then we can put different histograms in different blocks, right? So here what we are trying to do is let's divide the canvas into 3, right? So there are 3 histograms we want to draw. So let's divide it into 3. And then what we are doing here, this is interesting. So here, if you see, first of all, we are using enumerate, which is Python. And then we are looping over the elements of the branches array or list in this case. And we would like to start at 1. That means when you count, this counting is starting at 1. You can do that by adding this argument to this enumerate. Okay, so by default it will start at 0, as you know in Python. So lists, the first element of the list is 0. But let's say if you want to start at 1, then you can do this, and then I will be 1 for the first iteration. And why we do that? Because canvas, if you want to go to the first division of the canvas, we have divided it into 3 sections. And if you want to go to the first division, you should say canvas CD, then 1. That means it will go to the first division. Then 2, if you want to go to the second division. Why? Because obviously only when you are going inside the first division, there you can draw one histogram. And what we are drawing here, as you can see, we are not like we did it on the first day, that we were loading the tree and we were looping over all the events, and one by one we were filling one histogram. Here, everything is done in one line. The same thing is done, obviously, that it is looping over all the events and filling the histogram with all the information that we want, but that is written in one line, okay, which is obviously very good, right? So you don't need to write a lot of things. So, and for that, what you use is the draw method of TTree. So this is TTree, and you are using the draw method. And what you are doing is, let's say this branch name. So the first iteration, in the first iteration, you have lepton PT. So this will be lepton PT, and then you give 2 arrows. Then what will happen is this lepton PT is going to be pushed into a histogram, which is called hist underscore lepton PT, because this branch name is still lepton PT, lepton underscore PT. So all the data that is there in this lepton PT branch will be pushed to histogram underscore lepton PT. Now this histogram was never defined before. That means whenever you call draw, it's going to define that histogram also. But obviously, if you want to define it, you can define it before you run this draw. So you can define it here. You can say, okay, I want to create a histogram called histogram underscore lepton pt, or any histogram. And you can say that I will create a new histogram th1f, and you can call it hist underscore lepton, lepton pt, right? So, and then all the other arguments that you generally give, right? So you can obviously do that, and then you just pass this hist here, or you can also pass this name of the histogram here. But basically, then it's going to write the histogram in your into the histogram that you have defined. Otherwise, if you do it this way, it's going to just define a new histogram and put everything inside. Okay, this hist is basically telling that I want to draw it as a histogram, okay, not points. There are multiple ways of plotting a histogram. So this hist is one of the way. And then here you could have define some selection that, okay, I want to select only those events where lepton eta is below 0.2, let's say. So that kind of selection you can apply here, or you can also apply some kind of weights. Okay, basically this argument is for applying weights. But if you, as you can understand, if you define a selection here, then if that condition is true, then it will, the value of this variable for that event will be 1, and if that condition is false, then value of this variable in that event will be 0. Then if you multiply this 1 with lepton pt, it will become the same lepton pt. But if you multiply 0, then it will become 0. That means that event will be counted either once, or it will not be counted if the condition is true or false. And that way you can decide if you want to fill the histogram with some events, and if you don't want to fill the histogram with some other events. So that kind of selection you can apply. Or you can also say that, okay, I put 2 because I want to multiply. I want to say that each of the events has to be filled twice. Okay. Yes, I think there was some question. I don't know. No. Can I mute him? Yes. Okay. Now what we are doing, we have already defined the histogram. Now we can get the histogram, but where is this histogram? You don't know where this histogram is saved now. It's in the memory. So what you can do is you can go to the current directory, and then you can say that take that histogram or get that histogram from that current directory. And I am accessing that histogram as hist. Why? Because I want to do some styling on the histogram. Like I want to set the title of the histogram, I want to set the color of the lines of the histogram, and then I want to draw it. And where I am drawing it, I'm drawing it in the first section of the canvas. Then in the second iteration of the loop, it will be the second section of the canvas where I'm going to draw lepton eta, right? And this way I can draw with this loop this loop is running over this list, where in this list I gave some names of the branches, and what it gave me, it has created this canvas. Though it's, I think I zoomed it, that's why it's not good. But yeah, so this is what you get. So you have lepton pt, lepton eta, and lepton phi, right? So now, so this is done. Obviously, as you can see, I am only reading the signal tree. So these are the distributions in signal, right? Or in Higgs, in other words. So I call Higgs as signal.
Sir,
And then,
you
yes.
Sir, in the for loop you set start equals 1. So I thought that will mean that in the branches list, we will start from left and eta instead of left and
No,
pt.
no, it doesn't mean that. Because this is the argument to enumerate, right? Oh, sorry. This is an argument to enumerate, right? And what enumerate returns is basically a list. Okay, let's print it. Print enumerate branches, right? As you can expect that this should return a list. Oh, it's an enumerate object. Okay. But then you can probably convert it. But okay, so you do not need to convert. But basically, if you don't say start 1, then what enumerate returns is, or it is basically an iterator. It creates an iterator over this list, but then it returns this I and value of this one of this element of this list, right? So this I will start from 1, not that you get the second element of the branch. If you want, you can do this. If you want to do that, obviously you can do this, right? So that means you want to start from the second element of the branches list, right? And in that case, you will see only the last two will be drawn, right?
Okay, so it is like in the for loop, there is a buffer and we are overwriting the index of that buffer, like corresponding to that branch name. It was originally 0, but we are overwriting the 0 as 1.
No, it was not 0. As I said, that when you call this enumerate, it creates an iterator which returns this kind of, you can call it a tuple, I think. So where you have this I comma branch name, right? So if you pass an argument where you say start equal to 1, then in the first iteration, I will be 1 and branch name will be the first element of the branch. In the second iteration, I will be 2. It will be like increased 1 by 1, and then you will get the next element. So this is how it will work. There is no buffer here, and you are not replacing something by something new.
Okay, sir.
On the first call of enumerate, you are getting an iterator which starts with 1. It's not that it's giving you first, it's giving you 0 and then you are converting it into 1. It's not that. Okay.
So we are not actually getting the indexes of branches.
No, we are not getting the indexes. Of course not.
Okay.
That's not
Okay,
what
sir.
enumerate does. Enumerate never gives you the index. It will give you 2 things. First is an integer. Second is the list, the first element of the list, and then second element of the list. It will iterate over the list, but the extra handle that it gives you is this number, the counter, you may call. How many times this for loop is going. But that counter has nothing to do with the location of that element in the list, location of this element in the list. They can be totally separate, right?
Okay, sir. Okay, sir.
So okay, then what I tried to show you that this signal tree, you can also on the same canvas, you can draw the background tree also, right? And then you can see how the signal tree or signal histograms and background histograms, they look like. But as you can see, I have used those variables which are not that discriminating between the signal and background. Let's use one of those variables which are discriminating, like mjj. Okay, so let's put mjj here. And then maybe ml new. We are just randomly selecting some of them, obviously. And mwwbb, let's say. Okay, and you draw them. Okay, so as you can see that they have some distribution, but obviously it's not clearly visible. So what we can do is we can, because sometimes they go up, and that is why it is important to define your own histogram, because as you can see, the range and the binning is decided automatically by root. Okay, so if you
Sir, I
want
have
to
a question.
define, yes,
So,
please.
sir, just like in the root interface, we can put our pointer and zoom it in the range, what range we are. I mean, here we cannot do, correct? Because this will be
We
in.
can. It's not that we cannot do. We can, but I'm not going to show you how to do that today. But maybe if you want, you can check using JavaScript. It's possible if you load JavaScript in your Jupyter notebook. Then there is a feature that you can use to zoom into a particular region and etc. Okay, but then obviously in that case, yeah, so it will be slightly different, but the idea is the same. Now, one thing I wanted to show that currently, as you can see, we have same number of signal and same number of background. Because why I can say that? What I did is there is something called integral of an histogram, right? And as I'm creating two histograms, one is called his BKG background, his signal, and I'm taking the integral of each of these histograms and printing them, and I see that the integral of these two histograms are same. That means you have same number of signal as the background. So if you for some reason, if you see that one, sometimes what we do when we compare two distributions, we can also scale the histograms. Okay, for example, let me show you. So let's put 2 here. Okay, now you see, as I have given an weight of 2 for each event, that means each event is counted twice. That's why the background is now twice as much as the signal, right? And that's why, as you can see that, okay, let's do this. Let's put a hist here, because when you apply weight, yeah, so you see that this is going to the sky. Now, the reason why I wanted to show this is because what I can do here before I draw, just to show everything in the same canvas, or you can do the correct comparison only when you have the same number of entries in both the histograms. What I could do is I could scale the background histogram, or maybe if you want, I can also scale the signal histogram. There is something called scale, which is a method of th1f or th1 objects, because these histograms are th1, right? So, and you scale it by how much? So suppose you want to give it to, I mean, you want the integral of the signal histogram to match with the integral of the background histogram, right? So what should be the scale? The new scale, let's call it new scale or scale, whatever, sig scale. And then if you multiply the current entries of the signal histogram by this scale, what it will do? So currently the integral of the signal histogram is this. Now, if you multiply by this fraction, the value that you will get, or the integral that you will get at the end in the sig histogram, will be the integral equal to the background histogram, right? So if you do this, okay, there is nothing called hist underscore sig. It's his underscore signal. Okay. Look, now you brought the both distribution up. Okay, again, let's put hist here. So now you see that previously the background histogram was shooting up. Now it is not, because now both of them have the same integral. Okay. Or sometimes people normalize everything to 1, but I'm not going to that because there are details. Now let's come back to this, the main goal of this exercise, which is to train the algorithm. Okay. So for that, as I already have said, that we are using TMVA. And at the beginning, we are creating an object which is called data loader. Basically, this data loader will contain all the data that we are at the end going to use to train the algorithm. Okay, so that is called data loader. And I'm giving it a name which is called dataset, and that data loader is loaded as loader in Python. Then this data loader or loader, this has a method called add variable. And these add variables are the variables which you want to use to train your network. So you only pass those variables which you know are discriminating or which you want to use to train your algorithm. Okay. So here we are only passing these 7 variables as our discriminating features. Okay. So we are adding them one by one. And then there is something which we also provide, which is called weight. And this weight is generally provided for many reasons. There can be many reasons, but one reason can be that, as you already have seen, that there can be some kind of imbalance between the signal, number of signal that you have and number of background that you have. You may have produced more signal than background or more background than signal. Okay. So then what we can do here is that we can apply some weight to the signal so that at the end, the algorithm will see same number of signal as background, because we see that this is how the training is done, that sometimes if you have a huge number of background but very small amount of signal, it may not, the training will not be optimal. Okay, so it's better that you keep them of the same order, signal and background, number of entries that you have in signal and background. But there can be other reasons to do that also. Like sometimes, as we know that in the Monte Carlo simulation, when you produce events, even though you produce one event, but to finally what you would like to have is that your variables that you produce should follow some theoretical distribution. Okay, but let's say your distribution is Gaussian, but you produced, this Monte Carlo simulation has produced an uniform distribution. Then what you can try is that for each event you can apply some weight such that if that means basically transforming an uniform distribution to a Gaussian distribution. And for that, you, as you know, I mean, you can apply some weights to those events which are far away from the mean to very low weight, that even if when you add them, it will not become uniform, but it will become Gaussian. So you can tune the weights of each event depending on what is the value of this variable. You can tune the weights and you can make a Gaussian as, sorry, a uniform as a Gaussian. You can convert, right, by applying weights. So these kind of things are done, I mean, not exactly from uniform to Gaussian, but these transformations are done in simulations many times. Like you expect some distribution, but when you produce something else, but then you reweight the distribution so that you get the original theoretical distribution, kind of. But okay, I'm not going deeper than that. So you can have some weights coming from your Monte Carlo generator, okay? So which will be kind of, if you have signal and background, both simulation and from your generator, you can get some weights, you can apply them. But in this case, as we do not have such weights, we are just providing one. Okay, so I'm saying that all the signal events have weight 1, all the background events have weight 1. Okay, and what I'm using, you see, add signal tree. So this loader again has, so first I have added the variables, then I am adding the signal tree and the background tree, right? So once you add these, so then you will have in the loader, you have loaded the signal tree and background tree, and they have 10,000 events, each of them, right? And in the same loader, okay? And then we can, again, after loading the data also, we can apply some selection. But again, I'm not going to do that here. So I have kept them empty, but if in future you like, you can apply some selection where, like on the lepton PT, you say, okay, I want to take only those events which has lepton PT above certain value or below certain value, whatever. But the important part here is that then you call, which is again a method of loader, data loader, which is called prepare training and test tree. Okay, so what it does, so you provide your selections if you have any. In this case, we do not have any selection, so we just passed empty string. Then you say that how many events of signal you want to use for your training. Okay, and obviously the rest will be used for test. Now you can ask why the training and the test. There is a reason. Again, as I'm not teaching machine learning to you, I'm not going into the deeper details, but just one line I would like to say is that to see that your training is applicable to any unknown data, we generally keep a part of your training data as a test data, or I shouldn't call it training data, but part of your input data set where you know the actual level. We keep part of it as your test data set where you you kind of mimic that test data set as unknown data set. Whereas even though you know actual levels, but you still would like to test your trained model on that test data set to see how that performs on the test data set. And only if the algorithm performs good on the test data set, you call that algorithm a good algorithm. Otherwise, if it only performs very good in the training data set, but whenever if you ask it to perform on the test data set, it fails. That means there is something called overtraining, which I'm not again going to discuss, but at least I probably gave you some idea about why we separate the data set, we break the data set, divide the data set into two sets. One is called training, one is called test, right? And then we do the same for background. And okay, so then there is something called split mode equal to random. And we do this because we want to, mix the data randomly. Mix in the sense that, as you have seen, that when we loaded the data, we first loaded the signal and then loaded the background. That means the first rows of this data set are all signal, and there are rows of the data set which are all background. You will learn in the next part of the school that this is, if you just use this for the training of your algorithm, it will fail because at every step, the idea is to improve your metric. For example, let's say you want to, when you fit a distribution using a function, which we have already seen, how the fit works. So it starts with some values of the parameter of the model, and then it calculates something which can be like gradient or something like that, or gradient of chi-square or something like that. But then it predicts, or it goes to the next point, next values of parameters, and it again calculates the chi-square at that point. And slowly at every step, it tries to decrease the chi-square, minimize the chi-square. And at some point, it will find the minimum of chi-square, and that tells you what are the best fit values of the parameters, right? So there are steps. Now, as I was saying, that suppose if you have your data set where the first set of rows are only for signal and second set of rows are only for background, then when the algorithm sees only the signal, it tries to make the parameters such that it can fit very well the signal, but at each step, then it learns how to match the signal very well. Now, if you show it all the background events, then it will try to modify the parameter value such that it can model the background very well. But at the end, if you finish there, then at the end, the model that you will get will be very good to identify background, but will not be very good to identify the signal, because it has forgotten all the information that all the knowledge that it has gained during the signal training, right? So that's why what we do generally is we mix the signal and background randomly, so that in one iteration maybe it sees a signal, then in next 5 iterations it sees background, and then in next 10 iterations it sees signal again, and it's like that, so that it doesn't try to focus on only one category. It can average out between the two categories, two classes that you have. Okay, so that will give you better result. Basically, that is what people saw. That is why we use this random splitting. And then norm mode number of events. So we just say that, okay, so you normalize the dataset, that means signal and background dataset, by a number of events. Okay, v false means verbosity false. That means it's not going to print anything when you run this. So it's only going to split the dataset. But if you want to see something, you can always do true. Hopefully. So, oh no, it didn't. Okay, something else happened maybe, but whatever. Sorry. So you created data set now, which are separated into a training data set and a test data set, but still it is inside the loader. You have not yet created two separate data sets. It is already inside the same data set, which is inside the loader. And inside the same data set, you have somehow tagged some events as training events and some event as testing events. Then what you do, okay, here I am creating a file which is called Higgs classification output.root, because I want to store some information in that. So that's not necessary for the moment, but yeah, it's just basically we are going to store all the outputs here. Then this is important. This is called the factory class of TMVA, which basically which you create, and at the end, this factory is what you will use to train your algorithm. Okay, so that's why you create an object of this factory class. So you give a name and blah blah blah, and obviously the output file name where the output of the training will be stored. And if you want the ROC, which I will come to, and this analysis type is classification. So there are, as you know, there are many kind of analysis. One can do regression, but here we are doing classification. I do not want to go into the details of how each algorithm works, but as we are using Fisher, so this is the part which is important for us today. So this is Fisher discriminant. And so you have to say, look, you are using this factory object, and what is the method that you want to use to classify the signal and background? We are using Fisher method. So here you mentioned that we can type K Fisher, and here you mention Fisher. Okay, that's the name. And okay, then there are many things which I am not going to discuss because that will take time. Suppose you added this, or you booked this method, you book this Fisher method, and then what you do, okay, so this is another method. I'm not going to go through them. So in this case, okay, did I do something? I changed something. What did I change? Use likelihood. No, I didn't change. Maybe I didn't run. Okay, use likelihood is not defined. So it was defined somewhere here. Why? Let me compile all of them, but maybe somehow I deleted something. Yeah. Okay, now it ran. Okay, so now you have created the factory, and the method that you want to use is Fisher and also MLP, as I mentioned already. And these are the input variables that we are going to use. Please stop me at any place where you have any question. So then what
Sir,
we are doing?
can you
Yes.
again explain? Tell me what was factory?
Yes, as I said, that factory is a class in root, which is obviously inside TMVA package, sub package. And this factory class is where you decide which algorithm to use. And this factory class is where ultimately the training will be done. I mean, this factory is basically the algorithm that you want to use and the training that you want to perform. All these methods, all these functions are defined inside this factory class. Okay. Like you had this loader where you just load the data and you split the data and etc., whatever you want to do with the data. So you apply some selection and you split the data into test and training, and you randomize the order and etc. Whereas this factory is the place where your algorithm is present, okay, which you want to then use this algorithm or factory to train on the data that you have loaded. I hope this answers your question.
Yes, sir.
So that is why you see that I'm now calling train all methods. Okay, someone can only train one method, but here this is the benefit of using root, because suppose if you want to use the same thing in Python, then maybe Fisher algorithm is defined in one package, BDT is defined in another package, neural network is defined in another package. But yeah, it is true that there can be thousands of packages where this neural network is defined. But then you have multiple packages and you separately use all these packages to do different kind of training with different algorithms. But here you can do everything at once, because root gives you this feature that you can train all the algorithms possible, at least which are there inside root, right? So that is the idea. So I can train all methods, obviously those methods which I booked already inside the factory, right? So that is why I call those booked method. Now, and then also you test all the methods, right? So you have the training sample, you have the test sample. So you train and then you test. And also you evaluate all methods. When you say evaluate all methods, it's basically evaluate over all the entries that you have in your input data. Okay. And if you run this, you will see, what is that? Yeah, here. If you run this, you will see many, many interesting things. First of all, it tells you what are the data sets that it has used, how many events it has used for training, how many for testing, right? And it also gives you some other statistical information, like in the signal, how the variables are correlated. And as you can see, there are some correlations between MJJJ 3 jets and M2 jets, and which is obvious, right? Because you are using the same information. Then there is this MWBB is one variable, and MWWBB another variable, and which are highly correlated, which is also expected. But okay, so you see some correlation between the variables, input variables, both in signal and background. And as you can see, as you know, I mean, obviously not all algorithms, but good algorithms not only look at the values of each variable, but also look at how they are correlated. And sometimes they can learn from the difference between the correlation of two variables in signal and background, and that they use to discriminate between the two classes. Okay. And you can also see this feature where it gives you the mean and RMS of these variables, right? So there are many statistical information that is present in the output. Okay. I'm not going to go over all of them, but obviously, as you can see, that it started training. The first part of the training was for the Fisher discriminant, and the second part was for, I don't know from where to where, but one part is for Fisher discriminant, one part is for MLP, right? Because these are the two things that we train. And then there is something called get ROC curve, which is again a method of factory. As you can see, the factory can do many things. It can also return you the get ROC, and obviously you have to pass the loader, and then you draw. So you see what this get ROC curve returns. It returns a canvas, right? So that's why you're storing it in a canvas. So directly it creates these ROC curves, and directly it returns the T canvas, right, object, and then you draw it. And then you compare between the Fisher and the MLP, and you see that one is better than the other, or how they compare. I would just like to show, as I have shown you this ROC, that this is the full form of this is receiver operating characteristic. There is a reason why it is called like that, because it came from the signal processing industry. So, but to us, I would like to emphasize what it means. So, as you can see in this box, you have all the events in your input dataset, okay? All the events, not only signal or background. It has all signal and background. But then you have a separation, this line. One side is signal and one side is background. No, not one side is signal and one side is background, but you have two classes. But then, okay, there is a question, I think. So how can we determine the appropriate percentage of data to allocate for training and testing? Okay, this is a very good question, of course. And there is no good answer to that question. So ideal situation is 70% for training and 30% for testing. But depending on the amount of data that you have, obviously you can sometimes do 50-50, because if you have a large amount of large data set, then even with the 50% of the whole data set, you can do the training. You can learn whatever you want to. So it depends, and ideally people try to optimize this percentage. Like they use 70, they use 80, they use 90, they use 50, and they see which one performs better. That means, in other words, how much training data you need to learn all the information, or not you, but the algorithm. How much training data the algorithm needs to learn all the information or most of the information. So that's kind of an optimization that one can do by changing this percentage. Okay, so that is what probably I hope I answered your question. So then what I was saying is that suppose you have all the data that you have, and then all these circles are one class and all these dots are another class. So let's say these dots are Higgs-like events, and these circles are non-Higgs background. Okay, but when you use any algorithm, you will see that that algorithm will correctly identify some of the Higgs as Higgs-like events, but it will also fail to identify some of the Higgs-like events as Higgs events. Or rather, I would say that it will also identify some of the real Higgs events as background events. Okay, so then we can call these two classes inside the Higgs class as true positive. That means it was Higgs, and the algorithm could also identify that event as Higgs. That's why it's called true positive. And then another class, which is it is Higgs, but the algorithm has identified that as background. That means false negative. False, that means it is wrong, and negative means identified as background, because all negatives are those events where the algorithm said that these are backgrounds, and all positives are those events where the algorithm said that these are Higgs. Okay, but then true and false are the actual labels of these events. So if I say true, that means whatever the algorithm said is correct, and if I say false, that means whatever the algorithm said is wrong. And that is why you see that if the algorithm says that these dots are not Higgs, that means these are false. And what the algorithm said is they are negative, that means their background. Whereas again, in this side, you see the same thing, that some of the backgrounds the algorithm could identify properly, and that's why we call them positive and false positive, because no, sorry, not identified properly, but it couldn't identify properly, sorry, that's why it is false. But yeah, so false positive, and then you have true negative. That means some of the background events which are background, and algorithm also identified them as background. So algorithm could correctly identify them. Now, there are two statistics that we can create out of these. One is called sensitivity and one is called specificity. So sensitivity is, as you can see, that how many Higgs events out of the whole Higgs events, how many Higgs events the algorithm could identify correctly. That means true positive divided by true positive plus false negative. Okay. So how many Higgs events that the algorithm could identify correctly over all the Higgs events. So suppose if there are 100 Higgs events, the algorithm identifies 60 of them correctly. That means it's 0.6 is the sensitivity, right, of this algorithm. Similarly, the specificity, which is the number of events, background events, which the algorithm could correctly identify, divided by the whole number of background events, right? So that means what? That you have 100 background events, and out of them, the algorithm could identify 70 correctly. That means this fraction will be 0.7. That means that is called specificity, which is 0.7. And obviously, our goal is to get both equal to 1, ideally. That means you want to create an algorithm which can identify all the Higgs events as Higgs and all the background events as background. That means both these variables or statistics, we would like to achieve 1, right? That will be the ideal situation, where all the backgrounds are identified as background, all the signals are identified as signal. Now, what is this receiver operating characteristic curve? Is basically you plot this specificity and sensitivity as a function of okay, this is something that I didn't explain yet. So let's go to this first, and then I will come back to that. So any algorithm that you, or any machine learning algorithm that you use, it's at the end will give you some probability, as I already said, of some events being Higgs and the same event being a background. Like that means the algorithm will tell you that, okay, this event has 90% probability of being signal. Obviously, then the 10% is being a background. Similarly, the algorithm for another event, it can say that this event has 80% probability or 0.8 probability or 80% chance that this event is background, and 20% chance is that this event is signal, right? Or 0.2 probability that this event is signal. So these probabilities, every machine learning algorithm will predict. Now we can draw that. the distribution of these probabilities. And as you can see that this blue, which is the distribution of probabilities for all the signal events, but then you can see that this is these plots are drawn using the labeled data set. That means I know that these events, all the events which are filled in this blue histogram, we already knew that they are signal. Now we want to see what is the probability of these events being signal. And as we can see that it's close to 0.6, but then it falls very rapidly. And then if we use background, but again, we ask the same question, that what is the probability of these events, these background events, to be signal, not background, signal. So that means we ask the same question, that for each event, what is the probability of these events being a signal? We could have also asked what is the probability of all of these events being background, but whatever we ask it for all events, for signal and background both. But we asked the same question, that what is the probability of these events being signal or being background? So in this case, we are asking what is the probability of these events being signal. So as you can see that there are many events in the background also, which has the high probability of being signal-like. That means our discriminator has not done a very good job. In this case, Fisher discriminator. That means using a straight line or a plane, it is very hard to define a plane which will easily separate the two classes of objects. That means we need another algorithm which may perform slightly better. And as you can see, there is before that, this ROC is produced using these distributions. So you apply selections at different places on this variable. So you start from here and then you start applying selections. That means you remove some events, and whatever is left, there you see how many signal is left and how many background is left. That gives you the fraction of signal and fraction of background that is left by applying that selection. And that is what we plot here. So we plot the fraction. So for any point in this ROC curve corresponds to one background rejection and one signal efficiency. So background rejection is basically 1 minus background efficiency, as you can understand. So this point has some background rejection and some background efficiency, which means that if you apply a selection at 0.3, that 0.3 selection will throw away some background and select some signal. So then you calculate the efficiency by which this selection of 0.3 on your output gives you for signal, and efficiency that this selection gives you on rejecting the background. That is what you plot here. And as you can see that obviously what we would like to achieve is something, a curve like this, which means this efficiency of background rejection for any amount of signal efficiency should be always 100% or equal to 1 if the rejection probability is 1. So that means you can totally separate the Higgs-like and non-Higgs-like events. But here, as you can see, that these algorithms couldn't do that. But at least what we can see is that MLP is doing slightly better than the Fisher algorithm. Okay, this is the end of this. And you can obviously go through this Python notebook and try to understand. And if you have any question, you can come back to me by mail. I will try to explain or answer your question. But those of you who are still here, I know, I mean, it's going late, but still I would like to finish with the last exercise, but obviously not going into the very details of all the lines, but giving you some idea about what we can do using uproot now. So last time, in the last exercise, we have everywhere we have used PyROOT or root, right? We have never used any other package. But as I said, that root itself has many dependencies. So at the end, Root is using those packages or those things, but not as many as what we need for uproot. As you can see, if we use uproot, we are loading NumPy, pandas, and then there is some other package which is called scikit-learn, sklearn. All these things, like, and again, for plotting, we use Matplotlib here. There are other packages also for plotting, but here we are using Matplotlib. So, and also for the Fisher discriminant, which sometimes also called as linear discriminant analysis, LDA, we are using this linear discriminant analysis of scikit-learn package, okay, which is one of the algorithms in scikit-learn discriminant analysis package, whatever. So scikit-learn is kind of, you can consider that as TMVA, but obviously they have many different features which one or the other doesn't have. Okay, so but it's similar, I would say. So again, you take the input file and you open the input file, but this time I'm using uproot. So first of all, I'm downloading the file, and to download the file, I'm using this URL lib.request. Okay, this is how you download the file. But as you saw that using root or PyROOT, you can directly use root to get the file. But here we have to use some other library to get the file, to download the file. And then we are opening the file that we have downloaded. And for that, we use this uproot.open, and then we provide the name of the file. And this is a feature of like Python or uproot, you can say, or obviously this can also be done in root, that if you open the file using this with, then the file as this is the name of the object that you are creating, which is file. So if you do this, then once this this section is over, this part of the code is you run this code and then you finish this part. So then you say signal data. This section of code, when it finishes compiling this part, it actually closes the input file already. You do not need to run like you saw before, that you open the file and then you close the file at the end after you do all the things. But here, if you open it like this with, then the file as file, then once this section of code is done, then automatically that file will be closed. You do not need to close it. So this is a good way of opening a file, you can say. But again, we are accessing the tree, but as you can see, it's slightly different than what we did before. So in case of PyROOT, when we were accessing the tree, it was slightly different. We were saying file.get, then the name of the tree. But here you can directly, like a dictionary, as you know. So because this file is a dictionary kind of, we already saw yesterday. Then we are loading the data inside these trees, and obviously here I'm only taking a subset of the data, or columns that I need. I do not need all the data. I do not want to load all the data, as we saw yesterday, that if we do that, sometimes it can overload the memory, right? So that's why I'm only selecting those features which I need for the training, right? So, and then I do this, I pass this variable, and then I say arrays, and if I do that, then it will return all the columns inside the dataset. All the columns means all these variables inside the dataset. And what I would like to have when it will return, I don't want to have an awkward array. In this case, I want to have a pandas data frame, which is many times used in machine learning whenever we do the training or do the processing of the data. We use pandas data frame. So that's why let's load it as pandas data frame. So I'm loading it and saving it into signal data. It's an instance of this pandas data frame, and background data, which is another instance of pandas data frame. And this contains the background data, right? So signal data, background data, I'm loading from the trees, from the input file. Then this is the feature of pandas data frame, that you can directly see what are the, and in this case you are showing the first 5. I didn't run the first part, so let me run them.
Sir, one quick question. So
Yes.
here, when we download this root file,
Yes,
so this is downloaded somewhere in our local machine, or I
of
mean,
course.
every time you run and every time it is downloading.
As you see, in this case also, if not OS path exists, only then I'm downloading it. Otherwise, if the file exists locally, it will open it. That means this code is not going to download the file every time you run it. So maybe the first time you run, it will download, and once it is there, next time you will run it, it will not go through this, but it will directly open the file. But yeah, it is downloaded in your current directory.
Okay, understand. In which directory you are working?
Yes, in which directory you have opened this file. So it should be in day 3, for example. I can see that. So I'm in day 3, and
Yes, it
yeah,
is.
so I have this Higgs underscore data, right? So this file is there. So yeah, as I was saying, that you then, if you just say signal data, it's going to show you this nice table. Okay. And then if you say, this is a feature of pandas data frame, that if you just say head, it's going to show you by default 5 entries, 5 rows, 5 events, whatever you want to say. Obviously, if you say 10, then it will show you the first 10 rows. Then let's say I would like to see the distribution of these variables. And before, you remember in PyROOT or in root, we had to loop over the branches, and every time we were filling the histograms and etc. But pandas data frame has already a feature that if you just say pandas data frame dot hist, it's going to draw the histogram of all the variables by default in a same canvas. Right, so you do not need to create a histogram, then fill the histogram, etc. But everything is done. You should remember this, that all this thing is done, what we saw last time in PyROOT. So creating histogram, filling histograms, drawing histogram, creating a canvas, then drawing histogram. Everything is done here also, but we don't see it because it is hidden inside the package. So you just call this function, and everything is written. Whatever we need to do this, to get this, is written inside this function, right? That's how it works in Python. So the same thing, also another feature, but in a different way, we can see that there is something called pandas data frame, PD, or pandas, not data frame, pandas. And then pandas has another method called plotting, and then you call scatter matrix. Okay, that is another function of this plotting feature. And then if you pass the pandas data frame, whole pandas data frame, then you see what it gives you. It's a nice matrix where you not only see the scatter plot between any two variable, but also you see the histograms in the diagonal. So that means this is how the MJJ and MJL new are scattered, right? So this is a nice feature. I like it. Sometimes if I would like to see how the different variables are distributed, I sometimes use that. So let me add. Okay. Let me add another cell below and look at the same, but for signal. And you will see that some features will be slightly different than the background. That is what we expect, right? Let's consider this corner box. Let's see if it is different or same. MWWBB and MJJ in signal is distributed like this. in background, it's distributed like this. Okay, it's slightly, for signal, it's slightly, diagonal, more diagonal compared to the background, which is very close to the x-axis. But okay, so you can play with it and you can check whatever you like. But these are the features. Different packages have different features. So like pandas data frame, they have this feature which you can use. Now, what we are doing, we are adding the label to the data because the labels were not already there in the input data set. So I am going to add the label. So I'm saying 1 and 0, 1 for the signal. And so I'm basically adding a new column in this signal data frame, right? Signal data is a pandas data frame where I'm adding a new column called label, and I'm inserting or assigning the value of all the rows of that column as 1. And just by writing this, as if I'm assigning a value on a variable a is equal to 1. It's not that. It's a whole lot of column. All the rows are assigned the same value just by this single line. And same here. So I'm assigning all the rows in this background data as 0 for this label column, right? And then I concatenate the two data sets. That means I concatenate the two pandas data frames. One is signal and one is background. And I reset the index. That means, obviously, as you know, in pandas data frame, probably I can show you. There is a column called index, right? This one, 0, 1, 2, 3. So if you say 0, that means it will return the 0th row, right? But if you, let's say, concatenate two such pandas data frame, then after certain rows where this signal will finish, then again this index will start from 0, right? Which is the background. You don't want that, and that's why you reset the index so that it goes from 0 to as many rows as it has. Okay, and you said drop true. That means you do not want to keep the original index. If you just remove this, by default, it will keep two indices. One is the original index, and one is the new index, which goes from 0 to the final number. But if you want to remove the original index, you can do that. But whatever. Then what you do, you say, okay, x, that means my input, which generally we consider any machine learning algorithm as y is equal to fx, right? And this f is the function that you want to learn from the data set. So this y is equal to fx, y is your output, and x is your input or input argument, and then f is the function that you want to learn, right? Using these algorithms. So that's why we keep the same kind of nomenclature, that we consider input features as x. We call input features as x. Output there is no output feature, but there is only one output, which is y in this case. And what is that? The label column, right? The label column is the output, and variables, we are using these variables, right? These 7 variables, which we also did last time using PyROOT, and we run it. And then there is something called train test split. You remember in PyROOT, using data loader also we did the same. We splitted the data set into training and testing, and then also we randomized. That means we mix the signal and background, right? So the same thing is done here, but in this case I'm using 70% of the data for training and 30% for testing, right? So what it returns is, it is returning 4 pandas data frame, right? Or NumPy, whatever you call. So so this X train, X test, Y train, Y test, they are pandas data frame. Now you are going to use X train and Y train for the training, where X train is the input and Y train is the output level, and X test is the input features for the testing, and Y test is the in output levels for the test dataset. Then you, as I said, that from scikit-learn, we have this algorithm, this method, which is called linear discriminant analysis. So you load it, call it LDA, and then you fit. This is how you do it. You just call fit, and that will fit. Like you remember in PyROOT, we were using train all methods, right? That was doing the training. But now here you say fit, and you pass the x's and y's, and that's how you fit it, right? Let me see if I run it. I don't know, probably not. Okay, I ran it, hopefully. Okay, now once this training is done, it's very quick because this is a very easy algorithm. So it needs very less computation. So then you want to predict for all the x's that you have in the training dataset. You want to predict the y for them, and for that you are using this predict method of the linear discriminant analysis, and that will predict the y trend. And again, you do the same for the test dataset, right? You get the y trend predict, y trend test predict. Also, you can get the probability of each of these datasets or each of these events being either signal or background. So for that, you can't call predict, but you will call predict proba, which basically returns the not the prediction. So if you do predict, it will give you either 1 or 0. 1 for signal, 0 for background. But if you say predict proba, that means you want to get the probability. Then you should call this predict underscore proba, which will give you the return the probability. Hopefully, I didn't run this part, so let me run it. Okay, and then if I again want to draw the ROC, so this is the rock curve, as you can see, and it should be similar to what we got using PyROOT or root. But as you can see, the axis has been switched. So I dedicatedly did this because I wanted you to play with it and then orient the axis and etc. and compare at the end if you want to go into the details. Compare this result with the other result and see if you get similar to what you got with root. And I checked and it was very close because the algorithms are very close to each other. I mean, the way they are implemented, basically. Yeah. So then I also wanted to check the, maybe I didn't run all of these. Yeah. No. Oh, yes. Whatever. This is not important. So this is the distribution of the output variable, but this is important. This part. So here I again plot the output distribution of signal and background. And again, the same question I asked, that what is the probability of all these blue events being signal, and what is the probability of all these red events being signal? And as again, you see that there is a large overlap. That means we couldn't find, using Fisher discriminant, we couldn't find a definite plane which can very well separate the signal Higgs-like events from the background, right? So that's all. I think we have spent 1 hour more on this, which is too much. And I know already many of you left, but okay. I hope I could give you some flavor of how uproot and PyROOT can be used for machine learning purpose. Okay. And obviously, uproot can not be used individually. It depends on many other packages that you need to install. Oh, I didn't mention that. Obviously, if the scikit-learn is not already installed in your system, you have to install it. If pandas is not already installed in your system, you have to install it, and only then you can run this, right? So, and how to install? I will update the README of my GitHub as soon as I can, of course. So,
sir,
yeah.
what is this import OS? I mean, in the last notebook also you said we will discuss in the later.
Okay. So as you can see, that there are few features of this OS package, not package, but yeah, it's kind of a library, OS library. So it has nice features that suppose if you give it a path, input path, or a path of any file in your system, which it will, as you can see, you are not, yeah. So it will. So if you say path dot exists, and then the file name or path to the file name, then or directory also. If you pass any directory as a string here, it will tell you if that directory or that file exists there or not. So these kind of nice features, if you want to use, you can use this OS library. Okay. But obviously this is not used for machine learning purpose. This is just for this small,
It is
text. Yeah.
for our convenience.
Yeah, of course. Yes.
Sir, can you again explain that last curve? I mean, probability versus density. Yes, sir.
Okay, as I said, that, I mean, again, we are going into the machine learning part, which you again and again hear during this school. But I didn't want to focus a lot on this. But I just want to mention that at the end, when you train your algorithm, machine learning algorithm or model, that model, then you are going to use to test on an unknown data set, which you didn't use for training, right? In principle, you should apply that model into unknown data set. But obviously here we are using the training data set and also test data set. Why we are doing this, we can discuss. But before that, I would like to say that what these histograms show us is that what is the probability of the signal events, which I know as signal, which are these blue. What is the probability of these signal events being predicted as signal? And as you can see, for some of the events in this signal data set, for which the probability is very high, which is close to 0.9, let's say. So that means the model is saying that, look, these events has 90% chance of being a Higgs. Whereas it also says that many events are there in this signal data set, which has only 60% chance of being Higgs. Right? And same for background, what it is saying that, look, there are many events, or not many, some events in this signal data set, which has very low probability of being signal. That means they are background like. They are, you can be sure that they are background almost. But there are also some events in this background data set which are very close to signal like. And that is why we are saying that this model would not do well in discriminating these two classes, because there is a large overlap, as you can see, in the model prediction, right? So the predicted score has a large overlap. And also that was clear from the ROC curve. So more you go towards this, that means when the true positive rate is very high, only then you can say that I could properly identify all the Higgs. But if the true positive rate is very small, that means you couldn't identify the signal as signal. Your model couldn't identify the signal as signal properly. So that's what we see here. But then just to come back to the question, why we are plotting both training and test, you remember I told you that generally this is standard in machine learning, that whenever you train with some data set and you keep another part of the data set which you will use as test, use for test, for testing. So then you try to find the probability in both training and testing data sets and see if they agree well or not. That means if the performance of your model is similar in training dataset and testing dataset or not. If they are not similar, then you are in trouble. Trouble in the sense that either you have learned very well about the training dataset, but that is the features that you have that the model has learned are not general features. They are specific to the training dataset. But if you consider any other general dataset, that feature is not there. But somehow from the training dataset, the model has learned that, and that is what we call overtraining. So using this, you can see if you see a large difference between the dotted line and the field histogram, that means the test, the probability distribution in the test and the training dataset, if you see a large difference, you can say that, no, my training was not good. Though, I mean, I don't know why the beginnings and edges are slightly different. I think I have to optimize that. But still, you can see that there the peak in the test dataset is slightly towards right compared to the peak in the signal, in the training dataset. So there is a slight change between the two. That means in this case, the training dataset, the model has learned something about the training dataset, which was slightly different or not general, and that is why it is not there in the test dataset.
Sir, is this what you are referring to as overtraining?
Yes, that's what I'm referring to as. So it's not always overtraining, but there can be the other side also, undertraining. But undertraining cannot be visible like this. I mean, if you just see the distribution in training and test, the only thing that you can see from here, that means the difference, if you see some difference in the distribution of training and test sample, you can understand that that means the test sample has some feature which was not present in the training sample, or the training sample had some feature which are not present in the test sample. And somehow the model could learn those features which are there in the training sample, but when it tries to apply that idea or that knowledge into the test sample, it is failing to identify the signal and background properly. That is what we call as overtraining. Right? I hope it's a bit clear.
Yes, sir. Yes.
I don't know.
And sir, one more thing, the processing, are we putting it into CPU or GPU? Like, where do we decide that?
Yes, good question. So as you can see, I mean, I didn't go to that part, first of all, but because I don't know how many of you have access to GPU, but if you look at the first exercise, where I have used PyROOT, there is a method which I have defined. I hope I can show you quickly. Yeah. So you see that BDT use MLP, and then this comes, there comes this GPU part. So use DL GPU if you have installed TMVA GPU, then you can do this. And as you can see there, you can pass, okay, here, TNN method name. Okay, so no, this is the name, sorry. This architecture GPU, and you pass this architecture GPU here. Where are you providing? Here, look, architecture. So if you say architecture equal to GPU, then for this method, obviously. So again, you see this book method, and what is the method? This DNN. So when you are doing a DNN, deep neural network, you are training a deep neural network with some number of nodes and layers. You see, there you can say that, okay, I want to use a GPU or CPU. And if you give these arguments, then either you will use GPU or you will use CPU. Okay, I hope I answer. And also, obviously, for other packages like, TensorFlow or Keras TensorFlow or PyTorch, they have different ways of accessing GPUs. So, but obviously, this is not what is the scope of my lectures. So I don't want to go into that. But yeah, it is possible. Only the PyROOT part I have shown, or the root part, but all the other Python packages, people are going to talk about them again and again in this series of lectures. Okay.
Yes, sir, and we don't need to mention anything specific to our system, like let's say the GPU model or something, right?
Obviously, okay, not here. Obviously, not here in the when you book the method, but when you install these packages, at that point, there must be some, I mean, when you install root or TMVA, it will kind of infer what are the GPUs available. When you install TMVA GPU, it will try to see what are the GPUs available in your system, and then yeah, so that's how it is. Basically, there is something called CUDA or this kind of packages. So yeah, there will be like a link between TMVA and the GPU that is there in your system. But in the code, you do not need to specify what is the model of your GPU or which company from which you bought the GPU and etc. In the code, you just
Arnab,
mention.
can I
Yes.
ask?
Yes.
But what you write here, the DNN method name, that's the model, right? DNN CPU or DNN GPU.
Yes, this is just the name of the model that you are going to create. It can have any other. It can have any other name. I mean, it's user defined. The important part is this one, GPU, this architecture.
But DNN method name is it just the name, or it is also the method that TMVA is using, like KBDT and these things, no?
Okay, so I think at least, okay, first of all, I didn't use TMVA to
This
train.
is TMVA, right? This is coming
Yeah,
from
this is obviously,
TMVA.
this is TMVA, yes. I have
The method name decides what method you are going to use in the TMVA, right?
Yeah, that you decide here. As you see, TMVA, T types, KDL, the deep neural network. But yeah, it is also true that probably, I mean, as I said, that I have never used GPU. So I am not sure if this is important. But as you are saying, maybe this is a general option and that you have to pass to tell not only this architecture, but also the method name where you have to say that either it is DNN GPU or DNN CPU. Probably. I am not sure. I have never run.
I am not sure. I've never used GPU, but yeah.
Yeah, exactly.
Well, like in case of TensorFlow, I think you have to use CUDA DNN instead of the
Yeah.
DNN if you want to run in
Yes.
the GPU.
Yes, maybe I can check and get back to you if you want to know. I mean, or we can, or if maybe I can also write it in the README.
Okay.
But my idea was not to show you exactly how the machine learning part works, but my idea was to show you how you can use PyROOT and uproot to get the data set and to in the workflow that I have shown you, how can you come up to this stage where you have all the input features and labels ready. And then this part was not my main motivation for this tutorial or lectures. My motivation was only up to here, how to apply selections, how to apply, how to get the features from the input trees and etc., how to process the data. And also I probably have given you some idea about how to use PyROOT and TMVA to do the training, and some idea about how to do the statistical analysis. That means how to fit, how to create a TF1 object and fit a histogram and get the best fit values of the parameters of the model. So these are the things that are additional knowledge that I wanted to give, but they are not the main focus of these tutorials. Okay, so if there are no more questions, maybe we can stop here. I am really sorry for taking much more time than all of you maybe imagined. So, but yeah, thank you for attending this, and I hope I could help a bit. So anytime if you have any question, just write an email. And as now the slides are almost like finished, I can send it to the organizers so that they can upload in the agenda, and maybe you can in future look at them and use them.
Yeah, thanks very much, Arnab. It was very nice set of lectures plus tutorials. I guess this will be very, very useful for them to start doing, any ML kind of analysis, because you need to use the root files as input always and make out the plots and all these kind of things.
Exactly.
Yeah,
So I
thank you
hope
very much.
they have all the knowledge to apply. I know that obviously they are not very confident, but still I hope they have the knowledge to apply
Yeah, I
it.
mean, this preschool is basically to give them, some advanced knowledge that they can be prepared to participate in the main school, where you will have the tutorials and so on.
Okay, thank you very much.
Thank you very much. Bye. Thanks again.
Bye. Yes.
So we'll see all the students again next week from Monday onwards.
Bye. Enjoy the rest of the school.